Hello, wonderful learners. Welcome once again to this channel. Here we study physics. Today we are looking at light wave, and precisely the topic is refraction of light wave. Of course, we know that refraction is a very important topic in physics. It cuts across both light wave and other forms of wave generally. So, what is the meaning of refraction of light wave? Refraction of light wave simply means the change in wave speed, wavelength, and direction of wave when that light wave travels between the boundaries separating two surfaces or media with different what densities. Okay, that is very simple definition, and you can see it on screen. Now, this light wave, as you can see, is moving from medium 1, making an angle I with the direction known as the normal direction, and on reaching the boundary interface, it bends away from the normal. It bends away from its actual course towards the normal inside a new boundary, as you can see. The angle it makes, the light ray, as you can see, is this one. The angle it makes with the normal inside the new boundary or new medium, that angle is called R, meaning angle of what? Refraction. Here, as you can see, is the second medium, medium 2. So, this means the light changes its actual what? Course or path, and takes a new what? Path in the second medium. So let us see, this concept of refraction is put forward into two simplified laws known as the laws of refraction of light. The first law of refraction of light is as follows. Now, the laws of refraction, the first one is as follows. The refracted ray, the incident ray, and the normal at the point of incidence, they all lie in the same plane. That is the first law of refraction. The second law of refraction, also called or known as Snell's law, states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, and that constant is a number that we so speak of. All right, it is constant for a particular pair of media, which means for light traveling from air to glass, or from glass to water, or from air to water, the ratio of the speed of light from air to glass, or glass to water, or air to water remains constant. Alright, for any air glass or air water or glass air interface. So we must bear this in mind, this constant value of speed of light in one medium to speed of light in the second another what medium. So the same will affect the wavelength. We must bear in mind that frequency of light does not change, it remains fixed for pairs of or pairs of media, as the case may be. So now we need to see this next law in a more robust way, as put forward by the man called Snell. Snell expressed this law in mathematical format as this: sine I, which is the sine of the incident angle, and the sine of the angle of refraction, R, okay, they have a simple ratio with one another, so that the constant called the refractive index or index of refraction is given the letter n. So the refractive index of medium 1 to medium 2 is written as 1n2 and is equal to sine I over sine r, also equal the same as the speed of light in medium 1 over speed of light in medium 2, and also the same as the speed of, sorry, as the wavelength in medium 1 to the wavelength in medium 2. So that those statements rather are expressed more robustly as sine I over sine r equal to V1 over V2, where V1 represents speed of light in medium 1 and V2 speed of light in medium 2. Similarly, lambda 1 is wavelength in medium 1 and lambda 2 is wavelength in medium 2. So that is that. So we note this. When light is traveling from a denser medium to a less dense medium, the light will bend away from the normal. But when the light is traveling from a less dense medium, such as air to glass, because glass is denser than air, the light will bend towards the normal. That means it changes its course closer to the normal. So that is for the direction. So we see this next law in a, let us see this next law rather in a simple example. Now, how do we apply Snell's law? Here's an example. A ray of light with speed of 3 times 10 to the power 8 meters per second in air enters a transparent medium whose refractive index rather is 4 over 3. Determine the wavelength of the ray in the transparent medium if the frequency of the ray is 1.5 times 10 to the power 10 hertz. So that's the frequency. So what do we need to do? We need to calculate the frequency. Sorry, the frequency is no. We need to calculate the wavelength of the wave. So to do that, we need to know the speed of the wave in the second medium. So let us proceed to the solution. Here, using the formula stated above, we shall write the refractive index, speed in medium 1 and speed in medium 2, wavelength in medium 1, wavelength in medium 2. Here we consider medium 1 to be air according to the question, and medium 2 the transparent medium not specified. That transparent medium rather could be air, sorry, could be other mediums such as glass or other liquids that allows light to travel through them. Now, first of all, we itemize the given information. The speed of light in air is V1 is equal to 3 times 10 to the power 8 meters. The refractive index of the media is given as 4 over 3. Speed of light in the transparent medium is what we don't know, so it is V2. Frequency of light is the same throughout, whether in medium 1 or medium 2, because frequency does not what change. So substituting this into the formula gives us 4 over 3 represents n, the refractive index in the equation. As you can see this equation here, this n will be replaced by 4 over 3, and v1, which is the speed of the wave in medium 1, will be replaced with 3 times 10 to the power 8, and then we have v2 underneath. And then if we are to cross multiply and solve, we will get 4v2 equal to 3 times 3 times 10 to the power 8. Eventually, we get 4v2 equal to 9 times 10 to the power 8, and divide both sides by the quotient of v2 to obtain a given value of 2.5 times 10 to the power 8 meters per second. So that is the speed. We now need to calculate the wavelength. Since we know the speed of light in the second medium and we know that the frequency does not change, then it is a straightforward matter to apply this equation of wave, which states that the wavelength is equal to the wave speed divided by the frequency, and which we write the wavelength is therefore equal to 2.25 times 10 to the power 8 divided by 1.5 times 10 raised to the power 10. And finally, we obtain a value of 1.5 times 10 to minus 2 meters as the wavelength of the wave. I must bear in mind that stated or used before, the frequency of a wave is the same for any pair of media. So thanks for watching. In the next video, we're going to have some teaser question on this theory of wave, this particular theory of refraction of light wave that you will solve. And also in subsequent video, we're going to still on this topic, we are going to be looking at refraction in a different way, where we will be considering objects placed under water or objects placed under glass, and why these objects appear to be closer to the surface than they actually are, or why objects placed in water or that transparent liquid appears to be bent, or appear that it look as though their shape is affected or deformed. Okay, these are all phenomena that can be explained can be explained using the concept of refraction of light. All this will remain available in the next video, so do well, watch out for the next video. Give the video a thumbs up if you really got something meaningful from this study. Do have a great time out.